Hello everybody, welcome into another lesson. So today we are going to talk about tangent lines to circles. We have our very first theorem here that states if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So here you have circle O with O at the center, and then you have line M, which is tangent to circle O at point T. That's T is the point of tangency. So according to this theorem, since line M is tangent to circle O, then radius OT, segment OT, is perpendicular to line M. That's all that theorem is saying. And then we have the converse of that theorem. I'm going to keep the same circle, but I am going to change it up just a little bit here. I'm going to write the converse. This states, the converse of the theorem states, if a line in the plane of a circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. So the first theorem stated that if you had a tangent line, if you had a line that was tangent to a circle, then it was perpendicular to the radius at the point of tangency. Now this is the converse of that theorem. It states if a line in the plane of a circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. So here we have circle O again, we have radius OT, we have this line M that touches the circle at point T. And line M is in fact perpendicular to OT. So let's state that. We can state that M is perpendicular to OT, therefore M is tangent to circle O. So since line M is perpendicular to radius OT, this theorem states that line M would be tangent to circle O. So those are pretty simple theorems to understand, honestly. Those really aren't that bad to understand. Now we have a corollary about tangent lines that's really going to help us with some exercises we're going to do today. Let's talk about the corollary that we're going to deal with. Corollary. Okay. The corollary to these theorems states that tangents to a circle from a point are congruent. And let me draw another helpful little circle here. Okay, so here's our circle. Here's point P, where the tangents start. Here's point A on the circle, where you could say that PA is actually tangent to the circle. And then we'll draw to a point B on the circle. So we have a circle here where you have two tangent lines that start at point P outside of the circle. They originate from the same point, and they touch two different points on the circle. Well, according to this theorem, the two tangent lines PA and PB are congruent. So we can say that segment PA is congruent to segment PB by this corollary. So if you have two tangent lines, or more than two even, that start at the same point outside of the circle, then those tangent lines are going to be congruent to each other, which we are going to use this today to for some exercises. Now, let's say I draw me a circle here, and then around that circle I set up some tangent lines in such a way that I can form a polygon around the circle. Yesterday we had talked about a polygon inscribed inside of a circle and a circle that's circumscribed about a polygon. You can have the reverse scenario too. You can have a circle inscribed in a polygon that's formed by taking three or more tangent lines to the circle and going around the circle. You can have that. And then that red triangle you can say is a polygon circumscribed, because think of circum means around, so it goes around the circle, circumscribed about a circle. So you can actually see that too. So not only can you have a polygon inscribed of a circle and a circle circumscribed about a polygon, you can have it reversed based on tangent lines, where you have several tangent lines that touch to form a polygon, where you have a circle inscribed in a polygon, and then you have a polygon circumscribed about a circle. So that's something important to keep in mind as we're talking about tangent lines. Okay. Alright, so now we're going to talk about we're going to talk about more tangent lines. So let's see here. Let's draw an even bigger circle. Alright, so as you see here, we have two circles where their centers are connected, and then you have an internal tangent here. You have between point A to point B on the next circle, you have a tangent line that's actually tangent to both of these circles at these respective points. If you have a tangent line between the two circles, that is called an internal tangent. If it goes between the two circles, that is called an internal tangent. So think of it internal, inside, and between the circles. And another property of internal tangents is that it intersects the line that joins the centers, as we can see here on this diagram. So internal tangents intersect the lines that join the centers of each circle together. So that's an internal tangent. Now we're going to talk about an external tangent. You fix this up a bit here. So this time we still have two circles where their centers are connected by a line, right? But we have a tangent line to both circles that touches at points A and B on each circle that does not intersect the line that joins the center of the circles. If you have that scenario where the tangent line does not intersect the line joining the centers of the circle, that is called an external tangent. So internal tangents go in between the two circles and they intersect the line that joins the center of the circles. External tangents are still tangent to both circles, but they do not intersect the lines that join the centers. So those are also important things to consider and keep in mind. Now, not only can lines be tangent to circles, but circles can actually be tangent to other circles, believe it or not. They absolutely can. So let's go ahead here. Let's draw some tangent circles. Okay, so we see these two circles touch, right? So they touch at one point. When you have two circles that are outside of each other touching at one point, these two circles would be externally tangent. So if you have two circles that are outside of each other and they touch at exactly one point, they are externally tangent. So circles A and B are externally tangent to each other. Now, let's give you another scenario though. Let's create a big circle here. Let's make that a little bit smaller, eh? For what I'm actually trying to illustrate. Now, let's say we had a circle inside of another circle, but that circle that's inside of the circle touches the one circle at, so usually it's going to be a smaller circle inside of a bigger circle. If the smaller circle is inside of the bigger circle and touches the bigger circle at exactly one point, it's still tangent. But since it's inside, these two circles are internally tangent. So circles can come, if they're going to be tangent to each other, they come in two varieties. Either externally tangent, since they're outside of each other and they only touch at one point, or you could have internally tangent, where you have a smaller circle inside of a bigger one, and the smaller circle touches the bigger circle at exactly one point. That's internally tangent. So those are very good things to know about tangents, that not only can lines be tangent to circles, but circles can be tangent to other circles too. Alright, we're going to do a few exercises here about tangents. Alright. Draw a nice big circle so we could see exactly what the heck we're talking about. This will be point O up here for the origin, for the center. Alright, let's label some points here. So we have a nice circle here where we have two radii that ultimately form a triangle. Well, what do we know about, we can see that line segment JT is tangent to circle O at point T, right? What does that mean exactly? That's going to mean that JT is perpendicular to OT then, since a tangent line is perpendicular to the radius of a circle at the point of tangency. So we actually have a nice right triangle now. So we're going to do a few exercises here and solve for lengths. So let's see, we are given that OT is equal to 6, JO equals 10. Find JT. So we got some lengths here. We have that OT has a length of 6. We got that JO, the whole JO here has a length of 10. We need to find JT. Well, this is nothing more than just doing Pythagorean theorem to solve for a right triangle. So you can apply these principles also to right triangles. So what we're going to do now is set up Pythagorean theorem. We will take the side JT to the second power plus OT to the second power, which would be 6 to the second power, set that equal to the hypotenuse of JO to the second power, which would be 10 to the second power. So then you would end up having JT to the second power plus 36 is equal to 100, which would then simply give you that JT to the second power equals 64, which means, since we only consider the positive square root, that JT, the length of the tangent line, would have to be 8. So yes, you can use right triangles to solve for lengths of tangent lines and other pieces too that originate from the radius and tangent lines. So that one was simple Pythagorean theorem. Alright, let's get rid of these lengths at the very least. Let's see what we get now. In this exercise, they give us that OT is equal to 6. This time, JT equals 10. Find, what do they want us to find? JO. So it's a little bit reversed. This time here we have the length of OT, which is the radius, has a length of 6. The length of the tangent line, JT, has a length of 10. We need to find the length of the hypotenuse, JO. So once again, set up your Pythagorean theorem. You'll take that 6 squared plus the 10 squared. That's going to be equal to the length of JO squared, which would then give you that JO squared is equal to 36 plus 100, which would then give you that JO squared equals 136 Hello. Hello? This is Matthew Bruce. Gotta hate those loan phone calls. Really gotta hate those loan phone calls. Sorry, everybody. That was pretty rude and inconsiderate of them. But anyway, I'm not interested in taking out a loan. But anyway, so we have JO squared ultimately is equal to 136. Well, we know 136 for sure is not a perfect square. But let's see if we have any factors of it that are. Well, if you take 136 and divide it by 4, you get 34 as another factor. So you could have JO is equal to the square root of 4 times the square root of 34. Well, we know for sure, we know for a fact that the square root of 34 has no way to break down any further, but the square root of 4 does. So the length of the hypotenuse, JO, would be equal to 2 times the square root of 34. And that's exactly what you would get. It would be just a little bit south of 12 if you did the decimal approximation. But basically you're treating this like a right triangle for now, using the fact that tangent lines to a circle are perpendicular to the radius. So that's how you can form a right triangle. Okay, a couple more exercises with this circle, then we're going to move on. Alright, so this time they give you that the measure of angle TOJ equals 60 degrees. What else do they give you? They give you that OT equals 6. What do they want you to find? They want you to find JO. Alright, so angle TOJ here is equal to 60 degrees. So we have a 60 degree angle right here. The radius OT is equal to 6. Well, you have a right triangle, and then you have a 60 degree angle as one of the acute angles. We know that the acute angles of a right triangle are complementary, so that means angle OJT would have to be 30 degrees. Angle J would have to be 30 degrees. So now we can actually very easily find the length of hypotenuse JO because we have a 30, 60, 90 right triangle. What do we know here? That the side opposite the 30 degrees is the shortest leg, 6. And in a 30, 60, 90 right triangle, the hypotenuse is twice as long as the shortest leg. So if you take 6 times 2, you would simply get that JO equals 12 by the 30, 60, 90 theorem. So yes, some of this old stuff is starting to come back, even in circles. All right, one more exercise with this. All right, let's see. They give us that JK equals 9. Just JK equals 9. KO equals 8. Find, this time you got to find the length of the tangent line JT. And at first this is looking really hard because you have two segments of the hypotenuse, JK having a length of 9, KO having a length of 8. They want you to find JT. Well, how in the heck are we going to find that? Well, look at your circle here. You have radius OK with a length of 8. Well, OT is also a radius, is it not? That would have to mean then that OT would have a length of 8 as well, since it's a radius. So now you know two of the sides of your right triangle. If it helps you to solve for JT, find the length of JO. Use your segment addition postulate. JO, of course, is equal to the length of JK plus the length of KO, which would be equal to 9 plus 8, which ultimately JO itself would equal 17. So now we have a right triangle where the hypotenuse has a length of 17 and one leg has a length of 8. We need to find the length of the other leg, which is the tangent line. So now set up the Pythagorean theorem. Take your JT to the second power plus the length of this leg, 8 to the second power, which would equal the length of your hypotenuse JO to the second power. That would be 17 to the second power, which means then you would get JT to the second power plus 64 is equal to 289, which would have to mean that JT to the second power would equal 225. Which then you take the positive square root, you would get a length for JT being the tangent line having a length of 15. So the length of JT being the tangent line has a length of 15. All right. I should have about 4 more exercises here. Let's make it a little bit bigger, eh? Let's come down some, though. Put a smaller circle in here. Then next to it, put a bigger circle touching it. Alright, so now we have 3 circles tangent to each other. We have a central point P. Where we're going to have several tangent lines. Alright, so as you see, we have 4 tangent lines that all originate from a single point. They give us, in this exercise, that PA has a length of 8.2. Tangent line PA has a length of 8.2. We need to find PD. They just want us to find PD. Well, do we remember that corollary that states that tangent lines from a single point are congruent? So if you have 2 or more tangent lines that all originate from a single point outside of the circle, they're congruent. So that means that PD would also have to equal 8.2 because the tangent lines all originate from the same point. So PD also has a length of 8.2. All right. What do we have next here? Do a smaller circle, then we shall do a bigger circle. Alright, so here we have 2 internal tangents to these 2 circles. You have tangent RS that is internally tangent to these 2 circles, and you have tangent TU that is also internally tangent to these 2 circles, and they both intersect each other. What do they give us? They give us that RZ, RZ, oh, that's the point where they intersect. They all intersect at point Z. They gave us that. But RZ has a length of 4.7. Then they give us that ZU has a length of 7.3. What we need to do now is find TZ and ZS. So we have our 2 internal tangents here where from R to Z has a length of 4.7 and then from Z to U has a length of 7.3. We need to find TZ and ZS. Well, these are internal tangents, but let's start here. Let's start at point Z, right? Let's consider the points of tangent C separate to each circle. If you just go from Z to T, ZT is tangent to the smaller circle at point T. And it's also tangent to the smaller circle at point R. What do we know about tangents outside of a circle from a single point? If they originate from a single point, they're congruent. So that's going to have to mean, if they're congruent, then that TZ would have a length also of 4.7. So when you have internal tangents, it's good to just consider from where the tangents meet and then focus on one circle at a time. That is your best way to beat these. Now let's go for ZS. Let's consider only the right half from point Z to the right. We know ZS is tangent to the bigger circle at point S, and ZU is tangent to the bigger circle at point U. Again, tangents to a circle that originate from a single point outside the circle are congruent. So if ZU has a length of 7.3, that also means that ZS would have to have a length of 7.3. So what you should get is that the length of TZ is 4.7 and ZS is 7.3. Alright, now I have two harder exercises here, but these will come up. So it's important that we do them and understand them. So we have a really big circle. This will be circle P. Then in here we have an overlapping circle, a smaller circle, which is circle Q. And then we have an external tangent here to circles P and Q, which is SR. So we have our externals here, SR, and then we have actually, this would be ST. My bad. This is ST, rather. We have the tangent line ST. It's going to go all the way out to a single point called R. And they're going to meet there. And then, of course, these connect. These all connect. Boom. I know it's probably not the best drawing, but here's point R. Alright. Let's see what we're given for lengths. We are given that QT itself has a length of 6. That would be the radius of the smaller circle. We are given that TR has a length of 8. And then we have the whole side PR. This whole side of PR has a length of 30. Now let's bring that up a bit. So the whole side PR has a length of 30. So we need to find PQ. They want to know what PQ is. PS. And ST. So we have two circles here. We have the lengths of TR being 8 and the whole length of PR being 30 and the length of QT being 6. We need to find the lengths of PQ, PS, and ST. Well, what's the first thing about tangent lines in relation to a radius? They're perpendicular, right? They are perpendicular. And this would also be perpendicular also. I know it's not the straightest, but they're perpendicular. Which means here you're going to actually have a right triangle. You have the length now of two of the sides of this right triangle it's split in two, we need to find the length of QR, which is the length of the hypotenuse. So we know the length of the whole thing's 30. We're just going to focus on QR at the moment. So let's set up our Pythagorean theorem. Take the length of QR squared plus that 6 squared. No, QR squared, excuse me. That's going to be equal to 6 squared plus 8 squared. Which would then give us that QR squared is equal to 36 plus 64, which would then give us that QR squared equals 36 plus 64 is 100. So the length of QR itself would equal 10. So we found the length of QR. Well, we need to find the length of PQ. That's one of the things asked for. What about the length of PQ? PQ is just simply going to be the whole PR minus QR, which would give you a length of 20. So that should give you that PQ would be equal to a length of 20, right? If you take 30 minus 10, you would end up getting 20. So we solve for one facet of this. Now we still need to solve for PS and ST. Okay, so we do in fact have these split into a quadrilateral and a right triangle. But couldn't we argue now, could we not argue that you could combine these two into one huge right triangle, right? Because on the big circle, PS is tangent to SR at the point of tangency. So you actually have a big right triangle. Well, we notice that you have the smaller right triangle QR has a ratio of 10 to the length of the whole side PR 30. In fact, let's deal with that here. We have that QR to the whole length of PR equals 10 to 30, which would simply reduce to 1 to 3. What that means is the ratio of the smaller right triangle to the whole big right triangle is going to simply be 1 to 3. So, what we can do now to find the other lengths, to find, for example, ST, let's go ahead here and let's try to find, first we need to find the length of SR, and then we can figure out ST. So, if we have the ratio of 1 to 3, that means that TR with a length of 8 would correspond to the length of the whole SR. Which when you do the cross product, that means SR has a length of 24. Well, to find ST, you'll just take the whole 24 minus 8. That can only mean that ST would have to have a length of 16 in order to solve for that. So we found ST now to have a length of 16. So all that is left now is to find the length of PS, which, again, you have the ratio of the smaller right triangle to the ratio of the whole big right triangle. Well, we're going to solve for PS. Again, you have the ratio 1 to 3, which would mean you would have QT, which would have a ratio of 6 to PS. Well, to find PS, just do your cross product. You would get that PS equals 18. So this actually goes back to talking about inside of circles we had similar triangles. So we actually got to use similar triangles with proportional sides to solve for all these sides. So just because they're circles, don't overthink it. Granted, the tangent line properties of circles help us tremendously, but everything else we've learned is still in effect. So you still have all the old properties to call upon. That hasn't changed. And I got one more exercise, then we are done for the night. Alright, what do we got here? A little bit different. So here's circle P again. This time we have a smaller circle Q that lies outside of circle P. We have a line that connects the two centers. The length of the radius of circle P is 11. This length here is 3, and then the radius of circle Q also has a length of 3. So that's going to be important to note. And then you have a tangent line here, an external tangent. You have external tangent JK that is tangent to both circles P and circle Q externally. Let me label those in black. Now, of course, we can actually turn this into a quadrilateral. We can connect PJ. We can also connect QK. It'll form a nice quadrilateral. So, if the radius of this circle here is 3, that means QK will also have to have a length of 3, right? Since they're both the radii of the same circle. Okay. What they want us to solve for is JK. We ultimately got to find JK. And you're probably looking at this like, how in God's name am I going to find JK? Well, remember we have a trusty thing called auxiliary lines. First, let's start with the fact of what? The fact that tangent lines are perpendicular to the radii at the point of tangency. That's going to go a long way here. You're going to see why in just a minute. Now, we can draw an auxiliary line in such a way that we can form a rectangle and a right triangle. Because if you draw the auxiliary line that way, you'll now have a rectangle. Okay. So here, JP would also ultimately have a length of 11, right? JP would have a length of 11 because that's also a radius. So the whole JP equals 11. But we formed a rectangle here. So that means this part of JP would have to have a length of 3. This part of JP would have to have a length of 8 in order for us to get the full length of 11. And then, of course, since we have a right angle here, we now actually have a rectangle and a right triangle, which is going to help us. So the length of PQ, the hypotenuse, is what? 11 plus 3 is what? 14 plus 3 is 17. Then we have a leg with a length 8. We want to find the length of this leg here. So we'll go ahead, we'll call this leg length B. We'll take our B squared plus our 8 squared for the length of that leg, set it equal to the hypotenuse squared, which would be 17 squared. Which would mean then that you have B squared plus 64 is equal to 289, which would then give you that B squared equals 225. And of course, we only consider the positive square root, so the length of B would have to end up being what? 15. Alright, so the length of this leg here is 15. Alright, so we've addressed this leg of the right triangle, but we formed a rectangle here in the top part of it. What do we know about rectangles? That they're parallelograms, and opposite sides of a parallelogram are congruent. So on that logic, by that theorem, JK would also have to have a length of 15. Since opposite sides of a rectangle being a parallelogram are congruent, the tangent line JK itself would also have to have a length of 15. So again, just because you have circles and tangent lines, don't be afraid to use old properties too. If anything, these are actually, the new properties are actually helping you to know that you have right angles and can set stuff up that way where you couldn't before. So don't get too overwhelmed by these. So the next lesson we are going to talk about arcs and central angles of a circle. So I do hope everybody has a great night and take care.